Okay, today guys, I will talk about the third chapter of Pure Mathematics 1, and it talks about equations and inequalities. So the first concept we have is how to solve linear systems of equations containing usually containing two variables. And these such systems can be solved with two methods. We have a method called substitution and another method called elimination. We're going to see what they both look like within solving, but I would like you to know that the key goal or the main objective of these methods is that you try to isolate the system and you solve it with respect to one variable. So let's say we look at the system we have right now, the linear system we have. It's 4x minus 5. Okay, apologies for the abrupt pause, but yeah, as I said, the key goal of these methods that you try to isolate the system you have or the equations that you have such that you solve it with respect to one variable. So if we have 4x minus 5y equals 4, and another equation, 6x plus 2y equals 25, we would like to solve this and obviously get the values of x and y. And how can we do so? We could do so by, if we quickly analyze this equation, if we would like to eliminate one of these variables, either the x or y, they're obviously not of the same value. You have 4x, or like for the x, you have 4 and 6. They're not obviously equal. And same goes with 5 and 2. So we would like to solve it in such a way where we eliminate one of these variables and we're left with one of the other variable, and we solve it with respect to that. So I see that we have -5 and 2. A way you could easily solve this is by getting a common multiple between the two numbers. So obviously the lowest common multiple we have between 5 and 2 is going to be 10. So if we already know that fact, we can multiply the first equation we have by 2 such that we get -5y to be -10y. So what we do is first we multiply by 2. This is for the first equation. So we have 4x times 2, so it's 8x minus 10y equals, and what was the 4 times 2 is 8. Okay, this is for the first equation. If we look at the second one now, we have 6x plus 2, and as we agreed, the lowest common multiple is 10, so we'll have to multiply this whole expression, 6x plus 2 equals 25, by 5. So if we quickly do that, let's write times 5. So 6 times 5 is 30, so we have 30x. And obviously, please be careful of the signs. Positive 2y, so we'll have plus 10y equals 25 times 5, that's probably 125 if I'm not mistaken. Yes, 125. And now you just have a new linear system you could solve such that you could already eliminate one of them. So let me just remove this. So the way we could eliminate this is by actually adding the two expressions together such that we eliminate these two. So if we try adding these two together, we have 30 plus 8, we have 38x equals, sorry, I don't like how it's just messy like that. And you have 125 plus 8, that's 133. Let me just open the calculator quickly, yes. So now obviously we can just divide the two sides by 38 to get the value of x. So x equals 133 divided by 8. If we pull that up in the calculator, that's basically 3.5. We have x equals 3.5. So now we already have one of the values. And now you could easily substitute x into any expression. It doesn't matter. Obviously, I'll pick the easier one, which is the first one we have, 4x minus 5y equals 4. Let me just quickly write that down for myself. 4x minus 5y equals 4. So y will be 4x minus 4, all divided by 5 equals y, such that we have 4, 3.5 minus 4 all over 5, and that would be equal, if we just quickly write that up in the calculator, this whole thing will equal to 2. So we have y equals 2. And there we go. We solved this linear system by using elimination, such that we get a common multiple between one of the variables such that we can basically cancel them out, and you're solving the whole thing with respect to one variable. Now let's get another equation or another system where we could solve it by using substitution. Okay, let me just write it down quickly. Okay, now we have this linear system, 3x minus y equals 7, and 3x plus 10x plus 3y equals -2. So if we do go back to our previous steps that we made, we could easily find that, oh my god, we could get the first equation to be a multiple of 3 for the y variable such that we could eliminate it, but you don't really need to do that. Since this is already has a coefficient of 1 basically, so all we could do is just rewrite it such that it's all a subject of y. So we have 3x minus 7 equals y. And now we have the whole thing as a subject of y. Now, you see this y, we could just replace it, and we'll be solving the whole thing with respect to the x variable, since it's the only variable that there is. So now, if we do that, we'll be left with 10x plus 3, open bracket, and just replace it. I think so, yeah, it's 3, and then 3x minus 7. And this whole thing is equal to -2. See? And this is what substitution basically is. You're just substituting one of the variables, and the key goal, as I mentioned, is just to isolate the whole system to one variable, such that you solve with given respect to that. And now, okay, we could just expand the brackets, and if we do that, we'll be left with 10x plus 9x minus 21, right? Minus 21 equals -2. We could obviously gather the like terms together, so we'll have 10x plus 9x is 19x, and if we add 21 to each side, we'll have, I think so, 19 as well. Yeah, -2, yep, 19. So we'll have x equals 1, and this is our answer for the x variable. And now obviously we could switch, but we could not switch, we could replace any expression which has x with our given value, and we could solve for y. So obviously the easiest one we could do is this one, and we could just replace it now, and we'll have, let me just, yeah, y equals, x is basically 1, so we have 3 minus 7, if I'm not mistaken, right? Yeah, 3 minus 7, so that's basically -4. And there you go. This is the answer of y, and that's how substitution works. Okay, now we have a new question. We have this linear system of 3x plus ky equals 8 and x minus 2 ky equals 5, and we're given two requirements or two questions that we're supposed to solve. It says prove that x equals 3, and the second question is find k when y equals half. Okay, and obviously we can do that. It doesn't matter what method we'll use, it just asks us to solve. So okay, what we could do is obviously we could either use substitution or elimination. You know what, I'd like to, it says we have to find x first, so I'd like to eliminate ky altogether. So what I could do is multiply the first expression with we can multiply by 2 such that we can eliminate ky. So let's do that. We'll have 6x, it's positive, right, plus 2ky equals 16. And we have obviously the second expression as it is. We have x minus 2ky equals 5, right? Yeah, 5. And if we do solve that, and obviously this is for myself, 6x plus x obviously will be 7x. 7x equals 16 plus 5, that's 21. So x equals 3. So we could do x equals 3. And we already proved the first question and we answered it. Now, what does it want us to do? Okay, moving on to the second question. It wants us to find the value of k when y is equal half. So that's pretty easy. Since we already have the values of both expressions, let's just write the second expression, which is x minus 2ky equals 5. So already we have, first let me just change the pen color, sorry. We have x equals 3, so we can just write 3 minus and 2ky, so we have 2, and then the value of y, k, bro. Oh my god, equals 5. And obviously what we could do is these will cancel out either ways, so we're left with 3 minus k equals 5. So in the end, k equals 8. Wait. Okay, this is what you get when you're in a hurry. It will be 3 minus 5 equals k. K equals negative 2. Oh my god. K equals negative 2. So yeah, just a quick tip. Please don't be impatient like me. I solved it with a different equation in mind, and I just solved it based on that. So yeah, we already solved this question. We used substitution, and we kind of used elimination as well. So like yeah, that's how you use these methods to solve such equations. Okay, I was just tidying up the page I have for the notes. Second concept we have is something of the similar kind. However, we just have a quadratic form involved. So let's say we have an equation, and let me just write it. Okay, let's say we have such a simultaneous equation or set of equations. We have 2x plus 3y equals 13, and x squared plus y squared equals 78. What we could do is, obviously we have the power of 2 which is bothering us, so we can't really do any sort of substitution or elimination directly. However, as I said, the key goal of either of these methods is to isolate the system and solve it with given respect to one variable. So what we could do is either get the first expression we have here to be either fully a subject of x or a subject of y. I'll just do it as a subject of y for the sake of habit. So let's solve for y here. So we have 2x minus 13, or no wait, actually we have 13 minus 2x, and we can just divide it by 3. So we have y equals 1 over 3, 13 minus 2x, and let's just simplify it and add the third into each number or each term. So we have 13 over 3 minus 2 over 3 x. Okay, so I just realized I solved the whole thing, but I was not recording. So now I have to just resolve it again. And I forgot to mention that in the end, they want like the question asks for the answers to be written in their simplest third form. So this is just something I have to keep in mind. So now that we isolated the first expression to be a subject of y, we can now just replace the y squared in the second expression here with this all squared. So let's do that. Let's just rewrite it. And we have normally x squared plus 13 over 3 minus 2 over 3x all squared. And just for myself, like for my own, like to make it easier on myself, I'll just write it twice. Because if it weren't fractions, I would be able to imagine the numbers or be able to calculate it mentally, and I'll find it with ease. But with this, like 3 as the denominator, is just giving me it's just mental gymnastics. So I'll just write it twice for myself. This, so basically x squared plus y squared all equals 78, if I'm not mistaken. Yeah, all equals 78. And now let's solve this. We obviously we have to do what we have to do first is expand the brackets. So you have x squared plus, and I'll write this in normal quadratic form. So I'll write the x squared as the first term and whatnot. So basically 2 over 3 all squared, because negatives either ways will cancel out. So I can just calculate it as if it's just a positive term. We have 4 over 9 x squared, and then we have 13 over 3 times negative 2 over 3 twice. So what I could write in the calculator is 2 times, like 2 bracket, 13 over 3 times negative 2 over 3 and close bracket. And this will give me the b term. So this will be negative 52 over 9 x. And lastly, 13 over 3 all squared. I think so 13 squared is 169. Yeah, so 169 over 9 plus 169 over 9. And either ways, both numbers are indivisible with each other. And there's no need for the bracket, I think so I could just remove it. And all this equals 78. Obviously, let me gather the like terms now. So we have x squared plus 4 over 9 x squared. So that's basically 13 over 9. I think so, right? Let me just make sure. 1 plus 4 over 9. Yeah, that's 13 over 9 x squared. And we could just cancel out these terms together now. We have negative 52 over 9. Okay, and there's nothing else left with it. And we could just subtract 78 from both sides. So 169 over 9 minus 78. We left with negative 533 equals 0. Okay, sorry for the pause, but England and Switzerland I'm playing right now as I speak, and Soccer, my favorite player, scored. So yeah, I had to obviously check. Okay, now that we simplified our whole our expression, it says it wants it in third form. Bro, okay. To be honest, what we could do is just to use the quadratic formula. And yeah, let's do that. So we have x equals negative b. So it's basically 52 over 9, because either is b in this expression is already negative. So 52 over 9 plus minus. Let me just open the square root. B squared. So let me just calculate b squared. Negative 52 over 9 all squared. So that's basically, oh my god, what are these numbers? Either ways, we're going to calculate it with the calculator. So 2784 over 704 over 81 minus 4, and we have one a and c. B squared and 46. We have 13 over 9 and negative 533 over 9. And just close the bracket, close the square root, my apologies, over 2a, all over 2a. And so we have 2 and 13 over 9. So let's simplify this term. Let's actually not... Let me see what will the calculator pull up. Will it pull up a third, or will it pull up just an answer with decimals? So we have 52 over 9. Let's calculate with plus square root 2704 over 81 minus 4 13 over 9 negative 533 over 9 to 13 over 9. Let me see what the calculator pulled up. Oh, it actually pulls up an answer with thirds. Okay, so we have 2 plus 3 root 5, and I'm guessing the other possibility will just be negative 3 and 2 minus 3. Let me put the minus. Yep, 2 minus 3 root 5. So these are your answers for this. This is for x. And now we could find any expression that is easy enough for us to simplify to, or like just replace x with. Oh yeah, we have this term. So now let's do... So wait, let me just keep these in a box for myself. And now we have y equals, is it 13 over 3? 13 over 3 minus 2 over 3x. So the possibilities of y, once that we replace x with two values, so we have 13 over 3 minus 2 over 3 times 2 plus 3 root 5. So we have 3 minus 2 root 5. And let me calculate the other possibility. 3 plus 2 root 5. Okay, well, I don't know why I'm using this. I don't know why I'm using a calculator to get the other answer. So yeah, these are the answers for this quadratic simultaneous equation. Let's solve another one so we can fully get the grasp of it. Okay, let's solve another, or like one more equation, one more question on simultaneous equations and when they're quadratic, so we can fully grasp it also. Let me just write it down quickly. Okay, we have this set of equations. We have the first as y equals 2 minus 4x and 3x squared plus xy plus 11 equals 0. Straight away, you could notice that we could substitute the y in the second equation with its equivalent in the first equation. So we could rewrite it as 3x squared. And let's just add, or let's just multiply the whole thing with x straight away, as we could see here. So we'll have plus 2x minus, what the hell? Minus 4x squared plus 11 equals 0. And obviously, let's just simplify the like terms together. So 3 minus 4 will have negative x squared plus 2x plus 11 equals 0. And we could obviously just solve it straight away. We could either just use the calculator or we could just pull up with the quadratic formula. But it wants our answers in third form. Okay. So let's just... Do I have space? Yeah, I do have space. Let me just write the quadratic formula. We have x equals negative b, which is negative 2, plus minus b squared, which is 4, minus 4, we have 11, and negative 1. So we can just write the 11 straight away. We don't really need to write or wait, this is right, -1, yeah. So we can convert the negative sign here to positive, and all over 2a, which is -2. So we'll have, let me just put this in the calculator now. We have -2 plus 4 minus 4 times 11 times -1, all over -2. So we'll have 1 minus 2 root 3. And obviously this second possible solution will be 1 plus 2 root 3. So these are the values of x. And now obviously if we substitute these values in any equation to get y, obviously easily substitute it here. So we'll have y equals 2 minus 4x, right? 2 minus 4x. So we'll have our first solution as, when you replace x with, let's say 1 minus 2 root 3. So we have 2 minus 4 bracket 1 minus 2 root 3 close bracket. We'll have -2 plus 8 root 3. And our second solution will be, when replacing negative with plus here, we'll have -2 minus 8 root 3. Yeah, -2 minus 8 root 3. So these are the values of y, and therefore we have solved the equation. And either way, the question wanted us to solve the equation, like the equation, or get the variables such that we have the form of the answer as a plus minus b root 3. So we have, what is it? We have a here, and we have b here, and we have root 3 in each one. So I guess, yeah, this is correct. And this is the concept of quadratic simultaneous equations. And keep in mind, whenever we equate any two equations together, let's say, let me just find an example here. Okay, we actually haven't got to that part yet, but let's say we have these two equations, and I first of all get these two equations to a subject of the same variable. Let's say I get these to be a variable of y, and also here I get this to be a variable of y, and since y is obviously going to equal to y equals y, obviously, so I could just solve the two equations together with respect to x and get the x values. This, and when you graph these two equations together, the x values that you get as a result of equating both of them together when you have y as their subject, such that they share the same subject, you're actually just getting the points of intersection. And we're going to get to see this more when we solve more questions of different concepts. But whenever you equate two expressions together such that they have the same subject as well, that's why you could equate them together. Graphically, this means that you're just getting their points of intersection. So I just wanted to clear that up before I move on. And to explain furthermore what I mean, when we equate two equations together such that once we solve them and we get, example, like the solutions of x or y, what we actually get is their points of intersection. So let's simultaneously solve this. And once we do graph them, we'll get to see that there'll be either be 1 or 2 points of intersection, depending on the discriminant, once we simplify this expression furthermore. And you'll get to see what I mean. So first of all, let's graph these two equations and see how many points of intersection there'll be. So if I were to simplify, or like get the first equation to be a subject of y, we'll have y equals 3 minus 2x. Okay, so this will basically have a negative slope, and the y-intercept will be 3. So if I were to just draw a graph very roughly, we'll have example 3 here, and we want to see if we equate y to be 0, we'll basically have 3 equals 2x, x equals 3 over 2. So when y is equal to 0, x will be 3 over 2. So we'll have, let's say 3 over 2 is going to be somewhere here, like just past 1. We have 1.5. Let me just get like a different color. Yeah. And let's say this is the graph. All right. So this is basically 2x plus y equals 3. And let's graph the second one. To be honest, I'm going to use a method to find the turning points. There's a method actually that we'll take later on to find the turning points. It's just that if you have like a quadratic equation, you could get its derivative, equate it to 0, and solve for the x values. And either way, there'll only be one since it's the turning point. So let's just get y dash of the second equation, or y prime, whatever you call it. It's just the derivative. X will be 2x minus 3, and yeah, that's the derivative. So, and then we equate this to be 0. So we have 0 equals 2x minus 3. So I think this will be the same thing. We have 3 equals 2x. So x equals 3 over 2. So at x equals 3 over 2, it will be like this. I think so it's a positive equation, yeah. And a rookie mistake while solving, so I had to re-record. Okay, now that we got the turning point of the quadratic equation we have here, it's x equals 3 over 2. So now let's plug in 3 over 2 into the original equation to get the turning, or the y coordinate of the turning point. So we'll have y equals, and let's just write this in the calculator. We'll have 3 over 2 all squared minus 3 times 3 over 2 plus 1. So we have a turning point of negative 5 over 4. All right. And now let's graph these two equations together on the same like graph. Let's say we have here, doesn't need to be perfect. So let's graph the y equals 3 minus 2x. So let's say we have the y-intercept here as 3. And when you equate in this, this side to be 0, this one I'm talking about, we'll get 3 equals 2x, x equals 3 over 2. I was saying, and x when y equals 0 will be 3 over 2. So let's just say it's somewhere around here. Oh wait, somewhere around here. And let's just graph it and kind of extend it downwards like that. And now let's graph the quadratic equation, and we already got the turning point. It's 3 over 2 and negative 5 over 4. So it will just be right below 1.5 by negative 5 over 4. I'm not going to be able to graph that exactly. So let's say it will just be somewhere here and here. And the left hand side, I know here it will intersect within the positive x region, but I not know about the left hand side of this. Like, I don't know if it will be like this, or I don't know if it will be somewhere like here, because either way I'm graphing very roughly, you know. So now let's equate both of them together. Let's equate 3 minus 2x. 3, what the hell? 3 minus 2x equals x squared minus 3x plus 1. Let's obviously gather the like terms together. So we can add 2x to each side, and we could subtract 3 from each side. So we'll be left with x squared. Let's add 2x, so we'll be left with negative x. Let's subtract 3, and minus 2 equals 0. So I know this, I can just roughly imagine to be x and 1 here as a factorization of this x, and 2 here equals 0. And if we look at the b coefficient, it's negative 1. So I could say this is going to be x plus 1, and this is going to be negative 2. So this means that the actual x solutions will be negative 1, negative 1, and 2. So now I know that in the left-hand side of this quadratic equation, it will actually intersect within the negative x region. So let's say somewhere around here. And now we know that there are actually two solutions, regardless of whether we calculate the discriminant or not. Because like either ways, it will be greater than 0. So we don't need to do that. So this is what solving simultaneous equations graphically looks like. Since I equated both of them, I actually got their points of intersection, which would be here, as I said, 2 and some y coordinate, let's say it's y1, and here it will be -1 and y2. So we could then solve for the bro. We could solve for the y coordinates since we already have the x solutions, and let's just input it in here. So we have y equals 3 minus 2x when x equals -1 and 2. So we'll have the possible solutions of y as 3 minus 2 and -1. We'll have 5, and we'll have 3 minus 2, 2, and -1. So these are the y coordinates. So we have the turning points as -1 and 5. And we have 2 and -1. So these are the turning points, and that's how we could say we could represent the algebraic work of simultaneous equations on the graph. Okay, we have this question where we're given, let's say, two equations, and these two equations intersect together at exactly one point. And the point, and like the idea of what I was talking about, the discriminant and how we could use it to determine how many points of intersection are there, well, we could use it in this one. Because either ways, even I think in the previous chapter, when we talked about discriminant, we could talk about how it determines how many roots are there, how many real roots are there within the curve. So we could use it right now. Once we equate both of them together, we get the final simplification of where we could find the points of intersection, get a discriminant, and get the value of k, which is very self-evident right now. So yeah, let's equate them together. We have already y as a subject for this expression, so we could just substitute it here. So we could do that. Let me just change the color of the pen. We have okay, bro. We have kx squared, right? It's kx squared plus 2x plus 1 plus k minus 2 equals 0. How much space do I have? Oh no, I have enough space. So we could do kx squared and 4x plus 2 plus 4x plus 2 plus k minus 2 plus k minus 2. And we could notice that the 2's will cancel out each other, so what I'll be left with is k equals 0. And this has the same form as a quadratic equation. So what I could do now is, since it already tells me that it has one real root, I could get the values of k. So I could just plug in b squared minus 4ac. I could determine that it will be b squared minus 4ac. And since it has one real root only, it will equal 0. So now let's do that. Let's plug in the values for it. B here is going to be 4 squared, which is 16. Minus 4ac, we have 4, and ac both are k's, so it will be k squared equals 0. So I can determine it will be 16 equals 4k squared. I can divide both sides by 4, so I'll be left with 4 equals k squared. So k could either be, positive or negative 2. But in the question it's mentioned that k is a positive constant, so I'll take plus 2 only as my answer. And by the way, this is in page 42. So yeah, now I determined that the value of k is positive 2. And now it asks us, it asks us to find the point of intersection with the new value of k that we found. So since I already have the simplified version of the two equations like equaled together, or that we solved them simultaneously. Oh no, wait. No, we didn't actually solve them simultaneously. We just substituted. Okay, let's now simplify this with the new values of k that we have. So we have 2x squared. What is happening? We have 2x squared plus 2y plus k minus 2, which is 0. So we have equals 0. We divide everything by 2. So it will be y equals negative x squared. Yeah, this is the simplified version of this expression. K is 2. So we have 2x squared plus 2y plus 2 minus 2, which is equal to 0. And now that we have both expressions in the form of y or as a subject of y, we could equate them together. So we have negative x squared. And we could just add minus, like we could just subtract this whole, multiply this whole term, by negative 1. So it would be negative 2x minus 1 equals 0. So we can just find the points of intersection for this, and it will be, I think so if we take negative common, we could take negative 1 common, 3x squared plus 2x plus 1 equals 0. So in the end, this is also equivalent to negative 1 x plus 1 all squared. So yeah, the solutions to this is x equals negative 1. So the turning point itself is negative 1 for the x coordinate. Because either is x negative 1 will be also repeated, so it doesn't really matter. So, where was I? Now let's find the y coordinate by, let's say, plugging this into this equation. So we have y equals to negative 1. Was it plus 1? Plus 1, yeah. Which is equal to negative 2 plus 1, negative 1. So we have, what just happened? Oh, it just brought me to a new page. 1 second. So we have the turning points as negative 1 and 1. So yeah, that's how you solve it, by substituting and solving simultaneously. And even if you want to really make sure, you could actually just equate these two together and get their points of intersection and whatnot. And just for proof, let me let me go to Desmos. This was for the previous question, which we had x squared minus 3x plus 1 and 3 minus 2x. You see, this is the turning point we have, and they have two solutions since they intersect at two different points. So yeah, this is solving quadratic simultaneous equations graphically, or even just normal simultaneous equation or linear systems. If you do equate them together, you're going to get their points of intersection. And yeah, let's go to the next topic. Okay, and lastly, we've reached the final concept of this chapter, which talks about inequalities. And we're going to start off with linear inequalities. obviously before I even like start solving, hope we do know what these signs represent. This basically means 2x minus 3 as a whole is less than 5. And obviously when you have such expressions like this, we have to find which values of x will correspond to as a whole will be less than 5. Obviously signs the inequality might change, you never know, but this is what it basically means. So if we were to solve this and we were to find which values of x as a whole in this expression, for example, or this function of x, we could say, will correspond to less than 5. So let's find out. So if we add 3 to both sides, we'll be left with 2x is less than 8. And obviously if we divide by 2 on both sides, be left with x is less than 4. So if I were to now just rewrite this expression, and let's just see, I'm going to let 2x minus 3 equal a function of x, or basically just another notation of it is basically y. So if I were to draw this graph, but I already did it in Desmos, but I just want to explain something. So now if we just rewrite the inequality with the new assumption that I've made, I basically just assumed f of x is less than 5. So what I basically just did is that the x values which are less than 4 in the original inequality that I solved will also correspond to y values that are less than 5. And you'll see what I mean once I load up the Desmos drawing of it. Yeah, you see, this is the graph we have, which is 2x minus 3. So at x less than 4, we'll see it right here, x equals 4. And if we look up to where it corresponds to in the y coordinate, it will correspond to y equals 5. And anything less than that, as I said, x values that correspond to less than 4 will also correspond to y values that are less than 5. So this is what linear inequalities actually, or like inequalities in general, represent graphically. So this was just my point. I just made an assumption that I could just let this whole expression of 2x minus 3 equal a function of x. So what I just did is that I now have to find the x values that will correspond to a y value less than 5. So let's solve another one, but in this case we basically have two functions. We have 4x plus 12 is greater than 2x plus 17. Let's solve this inequality and also represent what it looks like graphically. So like terms, obviously we could subtract 2x from each end, we'll be left with 2x, and let's say greater than, and we subtract 12 from both sides, so we'll be left with 5 here. Obviously send the coefficient of x to the other side, we'll be left with x is greater than 5 over 2. And if I were to also assume that each of these expressions are a function of x, so let's say this is like f of x is greater than, let's say, g of x, I'd like to know what this looks like graphically. And keep in mind, not like I'm not talking about this graph right now, which I'll draw. Let's say we have a graph like this, and let me just draw another one. We have a graph like this. Starting from the point of intersection here, anything within this region is going to be f of x is greater than, let's see, another function like h of x. Not talk about the ones we are solving right now, just in general. Let's say that the black, sorry, my earphone just went out, that the black line represents f of x and h of x is basically the blue one. You see where they intersect here, and then after the intersection, this line is greater than the other function because basically it's above it, so that's what it means actually graphically. So anything after the point of intersection in here will represent this inequality. So likewise, if I let me just erase this. Likewise, and I already had the thing already in Desmos, so you could see it firsthand. Let me just open up real quick. All right, the black function represents 4x plus 12, the red one 2x plus 17, and the blue region just represents the inequality that we already solved for in the end. So you see, at x equals, let me just go here, x equals 5 over 2 basically, anything after that point of intersection will represent that 4x plus 12 is, as a function, is greater than the other functions that we had, 2x plus 12, 2x plus 17, my bad. You see, because after the point of intersection, the black line is above the red line. But if you see at x less than 5 over 2, it was actually the opposite. 2x plus 17 was greater than 4x plus 12. So that's what it just looks like. And yeah, just one last thing, which I actually forgot. If we want to write these as our answers, like for solving exams, we have to write it in a notation, in a specific notation. So basically, to represent x is less than 4, we first of all have to declare which variable we're going to talk about, like with respect to. So we just start with x, then colon, and all you do is just rewrite the inequality that we found. So this is our answer. And same here in the other question. So x is greater than 5 over 2, so we just write the same thing. We declare which variable we're talking about, then x greater than 5 over 2. Let's talk about quadratic inequalities, which is basically the same concept, but the only addition is that we're dealing with quadratic functions. So if we were to solve this inequality, all we'll have to do is just send all this to the other side and be left with 0. So it will be 0 is greater than x squared minus 4x minus 12. And I don't like it writing like this, so all I can do is just just rewrite 0 to be in the other side. So we'll be left with this whole function being less than 0. And if we were to factorize this, which we easily can do so, we'll be left with x plus 2 and x minus 6, and all of this as a whole is basically less than 0. So at x equals negative 2 and x equals 6, this will correspond to values of y that are less than 0, and you'll get to see what I mean, because this is just basically the factorization. This is basically f of x being less than 0. So if we were to draw this function, and give me a minute. All right, I have each function or like possible like algebraic expression that we reached within this inequality. We have first of all the two original functions, and you get to see it for yourself. These are just their points of intersection, but this is not what we're looking for. We're looking for that the simplified expression of them together as a whole, as a new function, should be less than 0. So if we were to do that, let's first of all get the new function that we reached, and you'll see within x equals negative 2, or values that are less than negative 2 and 6, this will correspond to y values that are less than 0. So that's what the whole thing represents. So if we were to now write this inequality, after we drew the graph basically, this will just basically mean x is basically, for it to correspond to y values less than 0 within its function, it has to be between negative 2 and negative 6. The most important thing is that you just draw the new function that you have, and you get to judge from there which of the x values will correspond to y values being less than 0. Okay, second question we could solve is this function x squared minus 3x minus 10 is greater than 0. So if we were to draw this graph, let's actually try solving it. We get the solutions of x. We have 1, negative 3, negative 10. So we have the roots as x equals 5 and pretty sure negative 2, yeah. So these are the roots. So if we were to just, we have 5 and negative 2. And if we want to get the turning point, I'll just do the derivative and set it to 0. We have 2x minus 3 equals 0. So x equals 3 over 2. So at x equals 3 over 2, we could say it's somewhere around here, and we could just plug it into the main function. So it can get its y coordinate for its turning point. We have 3 over 2 all squared minus 3 times 3 over 2 minus 10. That's going to be negative 49 over 4, which is more than 12, I'd assume. So you could say somewhere here, for example, and here. So somewhere like this. So now, if we were to look at the inequality again, it wants the x values that correspond to this function being greater than 0. Okay. And if you actually look at the roots that we already solved, at these values, x equals negative 2 and x equals 5, you'll notice that when x is less than negative 2, the values of y are above 0. And also at x equals more than 5, you get to notice that also the values of the values of y that correspond to x greater than 5 are greater than 0. So now we actually have two inequalities here. And anything which lies within this region, x between negative 2 and 5, will actually correspond to y values being less than 0. So now the answer to this is basically x less than negative 2. And to write it in set notation, we basically just have to write like this in a bracket. And x greater than 5. So this is our answer. A new concept which I actually found interesting is this inequality. 6 over x is greater than 2. To be honest, there are two ways to solve this. I think so the intuitive way most students would solve this now is just to multiply both sides by x. And the thing is, this is quadratic inequalities we're talking about, and you'll get to see what I mean when you actually draw the graph. You have to multiply both sides by x squared, or if you're good enough, and I hope you guys are, you could actually just draw the function yourself. You could draw the reciprocal function of 6 over x and see which y values will correspond to greater than 2. And I'll tell you guys why it might not be very obvious at first hand if you were to just multiply by x. And let's actually solve it that way. Let's actually just solve it by such method that I just said. So it will be basically 6 greater than 2x. So it's basically 3 is greater than x. And now let's draw the original reciprocal function, 6 over x. And I hope you guys know the standard form of reciprocal function. It's basically something like this. Yeah, it might be a bit stretched because of the 6. However, but like this is just basically how it looks like roughly. And let's say that 2 is here. For example, just 2 is here. Okay, and now let's look at the inequality that we reached at first. X is less than 3 or 3 greater than x. And let's say that 3 is here. And you're just going to keep moving here. Because basically less than 3, right? So if we actually look at the graph, we'll find out that's not really true. Because if you look at the negative x region, the values of x that correspond to less than 3 actually aren't greater than 2. You see what I mean? If you look at the original function, these y values, which correspond to this function of 6 over x, don't actually correspond to greater than 2. So there is a range, there's a specific domain, or there's only a specific range of x values that correspond to this such inequality. So in reality, the true answer is, is that you either just look at the function and you could just deduce it from there, or you could just multiply the whole thing by x squared. So it'll be left with 6x is greater than 2x squared, and now you'll be left with 0 being greater than 2x squared minus 6x. And you can just basically draw this graph instead, and you'll find the actual answers from there as well. So there are multiple ways to solve this. So you could obviously just draw the graph of this instantly. You don't really need to factorize or whatnot. Yeah, you can get the roots. You just easily get to the calculator. You don't even need to factorize or do all of that. So you have 3 and 0 as the roots. You have 0 here, and you have 3 here. These are the roots. And the turning point, I'd assume, is just around the middle. And we'll just, or we could just solve its derivative. We have 4x minus 6. So 6 divided by 4, basically 1.5. As I said, it's actually down the middle. And so in the end, x equals 1.5. This is for the turning point. And if we were to just plug in 1.5 into the original function, so to get its turning point for and its y coordinate, we have 2 times 1.5 all squared minus 6 times 1.5. We left with negative 4 over negative 4.5. So somewhere around here. I know it doesn't look the best, but yeah, that's how it looks like roughly. So now if we were to look at it again, we want the values of x that correspond to 0 being greater than its y values. If we were to just rewrite this, it's basically 0, or like f of x being less than 0. And oh my god, there you go. You could see here, and let me just change the pen color for it to be more obvious. Between 0 and 3, this corresponds to y values being less than 0. So there you go, you solved the inequality. And as I said, this was just one way of solving it. Another way you could have solved this is by actually just drawing the original function, not in solving the inequality itself. You could just draw the graph, the reciprocal graph of this, and see that yes, x values being smaller than 3 will correspond to its y values being greater than 2. However, this only applies within its positive x region and not its negative. So there are two ways to solve this. If you understand graphs and you understand reciprocals and how they look like, and let me just quickly explain its standard form. Let me just quickly explain it. Reciprocals. Its standard form basically follows this form. We have a, and I'll tell you what all these variables represent. X minus h plus k. And it has to be with these signs as well. So basically, a is just basically, you could say it's amplitude in a way, in the term, and this will determine how much it will either stretch or compress. And h is basically the x asymptote, and it has to follow the negative sign. So it's basically, if it's x minus 3, so the x asymptote of this would be 3, for example. But in here, as I said, what is it? 6 over x, there's no h term, so it's excuse me. So it's x asymptote is basically x equals 0. X equals 0 is just basically being the y axis. So it's and also with k, if we look at the original function that we were solving, there is no k. So the asymptotes are just basically the axes, plural of axis. So axis, I mean, what the hell? I'm waffling. So yeah, that's basically the standard form of reciprocals. And to be honest, I'd rather you solve it this way, where you just multiply both ends by x squared. So you can get you can just get an easier graphical representation of where the inequality lies. Okay, now there are a few more little concepts here and there that we have left. We're going to solve 2 more questions, and this will cover the remaining stuff we have left. There is the shading the region that satisfies the inequalities, and there's just one more where you draw the actual graphs, or graphs given to you, and solve for the inequalities and just shade, I guess. So, but there's a key thing. You see where some inequalities they have the equal sign and some don't, where they're mentioned as equal, you actually represent it by a solid line. But if they're not equal and just either a greater or a smaller than sign, you represent it as a dotted line. So this is just something I wanted to clear up. So just a quick one. If there's no equal sign, it's dotted, and if there's equal, then it's solid. So now let's draw the inequalities we have and shade the region that satisfies all of them. So we have y is greater or equal -4. So y is -4 somewhere here, and it has an equal sign. So we're just going to draw it as a solid line somewhere around here. We have no idea what it's yet, where the exact region is, so we're just going to continue. We have x is less than 5. So let me just pick a different color. Let me pick like purple, I don't care. And let's say 5 is somewhere here. And it says no equal sign, so we're just going to draw it dotted. Hope I can do it perfectly. All right. What other expression we have left? We have y is less than or equal to 3x plus 2. So let's draw that. Let me pick a different color. Let's say red. We have 2 as the y-intercept somewhere here. And when y is equal to 0, we have, I think so it will be -2/3. Yeah, it will be -2/3. So let me just make sure. Am I tweaking? Y equals 3x plus 2. So when, let me just, 3x plus 2 equals 0. Yeah, x equals -2/3. Okay, so I wasn't wrong. And 2 somewhere here. -2/3, is it less than 1? Yeah, it's less than 1, so it's very close up here. It doesn't matter, let's just say till here is y equals 2. And x is greater than 0. So it's somewhere along here. And when we found where they all intersect together, and this is the shaded region in the end. So you just basically find out where they all box up in the end, such that it satisfies all the inequalities. So yeah, this is the region that satisfies all of them. This question I actually forgot to shade and extend the part of the region, which is also part of the inequality. I said you should shade the region which is boxed up between all of the expressions that you had. So it's all the way until here. So yeah. Now this is the inequality, and yeah, just apologize. I just woke up and yeah, I feel like I can't focus. I'll see if there's any more questions to solve, and if there is, I'll just add it in the notes, and you can just see the final version of it. And thank you. And mistake is that I actually forgot that. I forgot a lot, so apologies. But yeah, the shaded region is actually until here. As I said, it's x greater than 0, so yeah, just keep shading this region. So yeah, hopefully, I think so. There's no more mistakes here. And obviously, if there is anything that I missed, any miscalculations or anything, please let me know in the comment section. And yeah, now thank you for watching.